Welcome to screencast number 1 for electrochemistry. We'll start this screencast by revisiting a reaction that was seen in class and in lab, for that matter, the reaction between copper 2+ ions and zinc metal atoms. And if we have a solution of copper 2+ and add a piece of zinc solid to that, we very quickly see copper solid form on the surface of the metal, and the blue color of the solution fades as copper 2+ ions are used up while this process is happening, and zinc 2+ ions are produced and they're colorless, so we don't actually see that. So this reaction, zinc solid plus copper 2+ aqueous, makes zinc 2+ aqueous plus copper solid occur spontaneously. And if we look at the reduction potentials chart and look for where the copper reduction half reaction is and the zinc half reaction is, and go through the process of combining half reactions to get the overall reaction, copper is higher on the reduction potentials chart, so it's more easily reduced, so it will be reduced. And here's the half reaction for copper 2+ making copper solid and its potential. And then zinc is lower on the reduction potentials chart, so it's not as easily reduced, therefore it's going to be oxidized. And being oxidized, it's written as an oxidation half reaction, which is the reverse of the reduction half reaction, which means the potential has its sign reversed from -0.76 to +0.76. And when we add up these two half reactions, the electrons cancel, and we get the overall reaction and the the potential for this reaction of plus 1.1 volts. Okay, now doing that, it's a transfer of electrons from the zinc, which loses electrons, to the copper 2+ ions, which gain electrons. And transfer of electrons is energy that's very useful, but this previous reaction was not done in a way that is very useful because the transfer of electrons occurs at the surface of the zinc and it's really hard to harness. But again, as seen in lab, if we have a piece of zinc in a beaker with some zinc 2+ ions, and in a separate beaker we have a piece of copper with some copper 2+ ions, we essentially have in one beaker, or one half cell, we have the zinc both in its reduced and oxidized forms. In the other half cell, or the other beaker, we have copper in its reduced and oxidized forms. And if we connect these two half cells, or these two beakers, with an electrical wire, and then complete the circuit to allow charge balance using a salt bridge, we can actually get the electron flow to go from the zinc to the copper through this external wire. And then we can harness that to, run a light bulb or some other useful thing. So let's take a look at this process. The reduction half reaction has already been looked at, and this is what occurs. And that occurs in the copper cell. So copper 2+ ions are gaining electrons to form copper metal. In the other half cell, we have oxidation occurring. So zinc metal is losing electrons to make zinc 2+. That means oxidation, and that's occurring in this half cell. Now, the place where reduction occurs, or the the electrode where reduction occurs, is called the cathode, and the electrode where oxidation occurs is called the anode. So copper is the cathode, zinc is the anode. We add them up and we get a total reaction, as seen before. Copper 2+ plus zinc makes copper plus zinc 2+, with the potential now for the cell of 1.1 volts. So if we hook up a voltmeter, that's what we're going to read. Just as a note, this is a standard cell potential for that, so that's what it will read if we have 1 molar solutions of zinc 2+ and copper 2+. Electrons are lost from the zinc, so they flow from the zinc to the copper. And then negative ions and positive ions from the salt bridge flow as shown into the zinc cell and the copper cell respectively. So in the zinc half cell, zinc atoms are forming zinc 2 plus ions, so positive charge builds up in this half cell. Now negative charge from the salt bridge flows into that half cell to balance charge, and that allows electron flow to continue. Now similarly on the other side, copper 2 plus ions are forming copper atoms, so there's less positive charge in the reduction half cell, which means more positive ions from the salt bridge have to flow in to balance charge and allow the process of electron transfer to continue. The cathode is positively charged relative to the anode, which is negatively charged, and do note this is true for a spontaneous cell, but we'll later look at non-spontaneous cells, and the sign or charge of the cathode and the anode will be different. So just note, cathode is always where reduction occurs, anode is always where oxidation occurs, regardless of if we are dealing with a spontaneous or not spontaneous cell. And electrons are flowing towards the cathode, which is positively charged in this case. So electrons are negatively charged. They're attracted to the positive charge of the cathode would be one way to look at this. This is an example of a spontaneous electrochemical cell, and we have a new mnemonic, which is lose electrons, oxidation occurs at the anode, gain electrons is reduction, which occurs at the cathode. So Leoa, the lioness, says Gurk is a way to remember this. And now it's a lioness. So what I would suggest you do is the next example on the handout was a electrochemical cell using lead and lead 2 plus in one of the half cells and aluminum 3 plus in the other. So see if you can figure out which cell, half cell has oxidation occur, which has reduction occur, which is the anode, which is the cathode, which way the electrons flow, which way ions flow from the salt bridge, what's the cell potential, and all that kind of good stuff. And this will be revisited in class after spring break. Now, one other thing to note, this is an example, as mentioned before, of a spontaneous electrochemical cell. Spontaneous electrochemical cells are also called galvanic cells or voltaic cells. And if we have several of them put together, or even just one, then we have what's known as a battery. And one last thing to note, we often write what's called cell notation, which is a shorthand for an electrochemical cell. It's a lot quicker once you understand what it means than drawing the whole thing out. So in this case, the cell notation is Zn solid with a line, then Zn2 plus aqueous with 2 lines, Cu2 plus aqueous followed by 1 line, and then Cu solid. And the left side represents the reaction that occurs for oxidation. So zinc solid makes zinc 2 plus. On the right side, we have the reduction reaction that occurs, or half reaction. Copper 2 plus makes copper. Notice the electrons are not shown here. The general convention is we do oxidation, which is the anode, on the left, and reduction, which is the cathode, on the right. We show what we start with and what we end up with in the oxidation half reaction, what we start with and what we end up with in the reduction half reaction. The salt bridge is represented by a double line in between the two half cells, and then the phase boundary between the solid and the aqueous ions is indicated by a single line. So we have 2 phase boundaries, one on the oxidation anode side and one on the reduction cathode side. And that's it for screencast number 1.